Recording in progress.
Okay, let us start. All right, last week I said we do this tutorial question is on the relay auto tuning. We look at the question and then at the same time that will help us to revise the relay auto tuning that I taught last week. So now you have a plant and then it's connected to a relay. Basically under feedback control, so that would mean if you draw the block diagram, that will look like you have a GP, then you have a relay here is +1 and -1. All right. So this is E, and so the input should be E. So the output is U. This should be Y. And the standard closed loop. And as usual, for simplicity, we'll just put this as 0. So this is plus, this is minus. Okay. So which means U would be 1 or -1, depends on E, which basically is -Y. Okay, so this is equals to E. This is equals to E. Then use the describing function method to find the limit cycle. So two concepts I teach you. If you have limit cycle, that means that you have if you have oscillation here, then you will have a oscillation here. And since this is 0 minus this, this will be exactly the same as this, but is inverted. So that means that this looks like it's -1. It looks like it's a gain of -1. And describing function is a gain of the nonlinearity. So the gain of this, we call it N. And we derive the gain of the describing function is, I derived in the lecture as, if you go back and look, the describing function of the lecture in the lecture is okay, this is the describing function of the relay. And I derived the whole thing, and it is 4m over pi a. So what is m? M is 1 because it's plus and minus 1 here, it's plus and minus m. So pi a. A is the amplitude of the sine wave at the input. So which means go back down. Is 4m over pi a. All right. So in this case, what is m? M is 1. What is a? A is the amplitude of the sine wave here. Okay, so we don't know what is that. So in other words, as far as the maths is concerned, since this times this is equals to -1, so you have n times g equals to -1. All right. So, and since now g is operating under a sine wave signal. So all the S replaced by j omega. So is 1 minus j omega, 1 plus j omega, whole thing square. So you stick that inside here. And then with this equation, you can solve for your omega and your A. So I should write down what is A. A is this amplitude here, and this is a sine wave, so we should write as sine omega t. Or sometimes we like to write it as u, sine omega ut. It's just either omega u is just omega u is just the ultimate frequency, the frequency of the limit cycle. Okay, so now we look at the solution. Like what I say, you have ng equals to -1. N is 4 times 1 over pi. G, all the S is replaced by j omega, so you have this. So now you stick this inside here, and you stick this inside here. All right, then this equation will give you this equation. And then after that, this is a complex number equation, so you compare real parts. You will compare real parts. So you take this is real, this is real. You go and solve it. I think you compare the imaginary part. So this is imaginary, this is imaginary. All right. So you solve it, you will get A is pi over 2 and omega is equal to √3. So what does this mean? This means that the sine wave that I draw here, this sine wave that I draw here should be pi over 2 sine √3t. Okay? Because we solve A is pi over 2, omega is √3. So that would be the oscillation that you get if you have a relay stuck in here. Then find the ultimate gain and the ultimate period. The ultimate period is easy. It is the period of this limit cycle. So that's easy. Omega is √3. So you just do omega. The period is 2 pi over omega. So that is easy. What is the gain? The ultimate gain, it is the gain of this, whatever gain this has that produce the limit cycle or the sustained oscillation. So we say what is the gain of this? We say the gain is the describing function n, and since it is 4 pi a, and what is a? A we found is pi over 2. So that's it. So this gain will be the ultimate gain. So we stick in pi over 2 inside A here, then you will find the ultimate gain. Because what is ultimate gain? It's a gain. What is a describing function? It is a gain. So what is the ultimate gain? Is the gain that is here that will make sure that the whole system is in sustained oscillation or limit cycle. So what is the gain there that will produce this limit cycle? Is a describing function. A is pi over 2, so you stick it inside. I think the ultimate gain would then be calculated. All right, you put it inside here. This is 1. this A is pi over 2. So you stick it inside, you'll get a 2. So the ultimate gain is 2. Okay, part 2. Part 2, draw the phase plane trajectory. Phase plane trajectory is just x and y axis. You know, x axis is state, y axis is state. So this, first of all, you see this is a second order system. There are two poles. The first thing is we convert this into a state space form to get the states. Phase portrait is just x-axis is state, y-axis is state. It's just like when I teach you sliding mode, you know, x and y-axis is the speed and distance. So x1, x2. All right, for a two-state system, that kind of thing. So the first thing, we take this. We take this transfer function, convert into a state space form. So I converted into this state space form. Of course, state space of the describing function is not unique. Whatever state space you converted to, you just draw the x1, x2. That's fine. So I just see one example, you know, where we converted to this state space representation of the transfer function. So that's it. We'll draw the x1, x2 of this. The first thing you need to know is that to draw this state space, you know that u is sometime +1, sometime -1. All right. And if you look at the picture, the figure, you have G, you have your relay, we call this Y, we call this U, then 0, we call this E. Okay. So you know U is 1 if E is positive and E is equals to -y. So U is 1 if Y is negative. So U is 1 when Y is negative. Okay, very simple. If you want for Y equals to -E is equals to this. So which then instead of putting U here, I put now which is a function of Y. So if Y and then a function of Y, so a positive sign, I change it to a negative sign. So if Y now is positive, F will be +1. If Y is negative, F will be -1. It's just basically so that now U is plus or minus Y, depending on Y, on Y. If Y is positive, then F is 1. If Y is negative, then F is -1. So it's just that stick the plus and -1 inside here. So you will get this. Then now, once you get this, the standard solution is to use Laplace. So use Laplace, you do this inverse Laplace, you will get this. All right. And then this inverse Laplace, this Laplace, you will get this. After that, Obviously, this Laplace, you get this. And this Laplace, you will get this. Okay, since f is either 1 or minus 1, the Laplace of 1 is 1 over s, minus 1 is minus 1 over s. So it's just f over s. So these two, you solve the simultaneous equation, you get x1 and x2. And then you inverse Laplace, you will get this. Now the condition for switching when the relay switch from positive to negative and negative to positive is when y is equals to 0. Y is equals to, if you look at here, the state space says that y is x1 minus x2. Here says that y is equal to x1 minus x2. So you see, when y is equals to 0, when y is positive and negative, the zero crossing is at y equal to 0. It switch from positive 1 to minus 1 and minus 1 to positive 1. So the switching condition would be y is equals to x1 minus x2 equals to 0, which then gives this. Since you have x1, you stick x1, you equate to x2, you will get this equation here. Okay, so let us start drawing. We assume that at the start, y is less than, y is equals to 0. Y is equals to 0. All right. So, and the state x1, x2 is equals to 0. So you state all these 0, 0, 0, 0. And since y is 0, you look at what is f. So y is 0, f is minus 1. So you replace this by minus 1. You replace this as minus 1. And this as minus 1. So x1, x2 will now look like that. Okay, so at t equal to 0, you have this. So x1, x2 looks like that. Then you start to plot. So let t equal to 0, t equal to 0.1, 0.2, 0.3, 0.4, 0.5, you get x1, x2, 0.6, 0.7, 8, 0.8, 0.9, 1, 1.1, 0.2. So if then you draw x1, x2. So if you do that, you will get this. You will get this. This is x1, this is x2. x1 versus as t equal to 0, it is here, then t equal to 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Now, then so okay. Then you know the relay will switch from positive to negative to positive. So you want to find when it switch. So you go and look at. And the switching condition is this. x1 equals to x2. So you got this, you equate this to this, you will get this. Sorry, I have a typo here. This should be a separate line. This should be a separate line. Okay, so if you equate x1 equals to x2, you will get this. You solve for it, you get t equals to 1.3. If you do that, it says that at t equal to 1.3, the relay will switch. So Now, which means that here at this point, you see this is a 45-degree line. So x1 equals to x2. T is equals to 1.3. And x1 is equals to x2. All right. So now we draw up to here. Then the relay switch already. So at first, we started off as U is -1, or we started off as F is -1. So it switch means now F is 1. So now we'll put in F is 1 here, F is 1 here, F is 1, F is 1. All right. Then now we don't use the same clock. To make it easy, we use a clock that is called T1. So we use a T1 clock. So at T1 equals to 0, we start the new clock. So what is the initial condition? When we start the new clock of T1 equals to 0, actually the old clock T is equals to 1.3. So the old clock is at T equals to 1.3. So the new clock is actually related to the old clock by this equation. All right, when T1 is 0, T is 1.3. So at T1 equals to 0, what is the initial condition? We check from here, we put in T1.3, 1.3. So the initial condition should be 1.3 e to the power minus 1.3. So you stick that in. All the initial condition for the new clock. All right. So if you do that, you got all the initial condition for a new clock. Then now you got everything here already. This is the initial condition for the new clock. This is F is what we say was, now F is 1, so it's taking 1. T is now T1, so you use new clock here, same thing. So this equation and this equation now looks like that. So now, then you draw T1 equals to 0. Then you, what is x1? T1 equals to 0.1. What is x2? T1 equals to 0.2. What is x2? T1 equals to 0.3. What is x2? So you draw. So then you go and draw. So if you draw, you'll find that you will get this curve here. When you reach here, you know that you will switch. And this curve here, just to remind you, the clock for this curve is T1. And when will it switch? The relay, +1 switch or -1 will be when here. So this one is T1 equals to what? But you know that the condition is x1 is equals to x2, which is correct because it's a 45-degree line. So let's solve for where is this? You just equate T1 equals to T2 in the equation. You equate T1 you equate T1 equals to T2. No, sorry, x1 equals to x2. x1 equals to x2. So you stick that in here. You stick that in here. You will get this equation. You solve. The changeover is T1 equals to 2.1. So you know that you will reach here at 2.1. All right, at 2.1. Then your equation will change again. Then obviously we'll do, and then we'll find a new clock. So this will be the T2 clock. All right, how is the T2 clock related to the T1 clock and the T clock? So I think it is the T2 clock is related by when T is equal to T2 plus 2.1 plus 1.3. All right, because you start the T2 clock after 1.3 seconds, after 2.1 seconds. So when T equal to 0, the first clock is actually here, 3.4. Again, to make life easy, at T equal to 0, we find the initial condition. At T equal to 0, the T1 clock is actually 2.1. So we look, what is the initial condition? So it's 2.1 here, 2.1 here, 2.1 here. If you do this, that will be initial condition for your X2 and X1. So once you've got the initial condition, then you stick the initial condition here. All right. Then remember to find out for yourself, F now, just now we say is 1, now is -1. Switch over. So once you have that, then you have this T2 clock, then you start drawing. T2 equal to 0, 0.1, 0.2, 0.3, you draw X1, X2. Then again, the relay switch at T1 equals to T2. So you do this, T2 equal to 2.2. So if you do that, you will then draw and get this. All right. And here, at this point in time, we know that T2 is equals to 2.2. So, okay, now let's start the T3 clock. So this one will be the T3 clock. All right, and this is obtained. Again, this one is obtained when X1 is equals to X2. So T3 clock is related to the T1, T2 clock as follows. All right, it's obvious already. So when T3 is 0, the first clock is all this added together. Then the same thing, go and find what is the initial condition. Then stick in, then you go and draw T3, 0.1, 0.2, 0.3, 0.4. So go and draw, and then find when you switch at X1 equals to X2. And you switch at T3 equals to 2.2. So this is T3 clock. And then this switch at T3 equals to 2. Okay, then now we're going to find the T4 clock. Okay, the T4 clock. Same thing, T4 clock is related. Do this, then find the initial condition, that is when T3 is equal to 2.2, so you stick 2.2 here, 2.2 here, 2.2 here, you get your X1, X2. So you get X1, X2 is this one. Then you find that the initial condition for the T4 clock is minus 0.4. It's the same initial condition for the T2 clock. You see the T2 clock. Initial condition is also minus 0.4. So you have the same equation with the same initial condition. All right, you can check that you have the same F. So the x1, x2 solution for the T2 clock and the T4 clock will be the same. So you already draw the T2 clock already. This, and since they are the same, so T4 clock and T2 clock is the same. And then you know E which is the same, then the N here will be the same, then here will be the same, so it will be in limit cycle. So the thing will cycle and cycle and cycle. Okay. Next. So now this is accurate, no approximation. I didn't use any describing function. When I use describing function, in the derivation of describing function, we use Fourier series approximation. All right. This one we didn't use describing function. The U was solved as +1 and -1. U was solved as +1 and -1. U wasn't approximated as a sine wave by describing function. So this is exact. So now the next question is, okay, so this is exact. The result in part B is exact. So go and find what is KU and TU. TU is easier. It's the period of the oscillation. So when it is at steady state, what is the period of the oscillation? You can look at the picture. It's easy to see. From here to here is 2.2. From here to here is also 2.2. So basically, it is 4.4. All right, when it cycle in the outer loop here, is 4.4. So 2.2 times 2. All right, so this is the easy part. 2.2 times 2. Find the ultimate gain formula was done using this. So what is A? A is the amplitude. So now with this, Y is x1 minus x2. So you take the T3 clock, which is already at steady state. You find the maximum. You dy dt equate to 0 is at 0.7, is at the maximum. So Y max is equals to this. So which means the amplitude of the oscillation is this. So you stick that inside. You will get KU as this. All right. Part 4. Ask you to find the period of the oscillation with no approximation. Question 4. This accurately. So last week I teach you, if you want to do this accurately, all you need to do is take the transfer function, do a zero order whole discretization. So we do that. Last week I taught you. We go back and see. Here we just look at the solution. Do a zero order whole discretization. You do, this is the plan. We do a zero order whole discretization. It is here. Then the next step is, every time you see a Z, replace by -1 and then equate to 0. All right. If you do that, so which means every time you see a Z, you put a -1. So you put a -1, you put a -1 of then square, you put a -1, you put a -1. So and then you equate to 0. So after that, you equate to 0. So this is there's only one unknown h. So one equation, one unknown, you solve for h, it gives you 2.178. And if you multiply by 2, this would be the exact period of the oscillation with no approximation. All right, question 5. All this, you get sustained oscillation if you stick in a relay. You also, traditionally, when they didn't discover that the relay can give this sustained oscillation, they actually put in a proportional gain. All right, so replace the relay with a gain and find Ku and Tu, which means, okay, don't use a relay, use a gain. So what value of gain would give you the sustained oscillation? So don't use a relay, but use the gain. So, which means don't stick in the relay, just stick in the gain. So which means for this question, the figure would look like that. Stick in a gain. Okay, the value that gives sustained oscillation, which means this is called ultimate gain. So what is the value that? This one we know. If you do the closed loop transfer function, it is y over r. If this is r, this is y. This equals to okay, there's an easier way. You can don't even care about the closed loop transfer function, because like I tell you before, if here is sustained oscillation, this should be -1. So you just take that in, do this. So replace this G by all the S inside G replaced by J omega. You got this. So you got this equation. You just solve for real part, imaginary part, you will get this. So if you put a gain here, your ultimate gain will be 2 and the period will be 3.6. The exact one is the one that is produced by the relay is 4.3, but if you put in a gain, then it is 3.6. In the past, before they use relay, they always just use a gain. All right. It's only, maybe 20 years ago, then they begin to use the relay. Research discovered that relay can be used for this. Okay, go for a break, then come back, then we do question 6. Come back at 7:10. Okay, question 6 is like that. Question 6 is find the describing function of a relay with amplitude m and hysteresis h. Now, so far the relay that I draw for you all looks like that. They all looks like that. All right, m and minus m. If the input is a sine wave, then the output from here to here will be positive m. Then from here to here will be a negative m. All right, but in practice, you always have noise in the system, so you don't get a pure sine wave. What will you get in the industry? The signal E or Y will not be a sine wave, but there will be noise. Noise here is not important, but if you have noise here, then that will be a problem. You see, when here it will still be positive m, then suddenly here, because of noise, it becomes negative, so you come to a negative m. Then because of noise, you jump back to positive, so you go back to a positive m. Then because of noise, you go back to negative m. And then you continue with negative m. So every time you have a zero crossing because of the noise that cross over from positive to negative, you will have a chattering, zap, 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 like that. So, and then you know the equipment was small, you have valve, valve, pop, like that. So in practice, the industry, they will implement a relay with hysteresis. Means what? It's like that. It's like that. That means that if this is very positive, this area here, it will be positive m. So let me so if I start from here, this part is very positive, so which is here to here, it will definitely be positive m, so no problem. So here to here will be positive m. Then over this part, when it is not so positive already, it will still continue as before. So it will continue as before until it reaches this part when it is very clear that it is definitely negative, then only will it switch to negative. All right, so same. So when it's negative, up to here, back here, it is negative. Then from this part to this part, it is not so sure. It will continue as before. So since it's negative, it will stay as negative. Then once it crosses this path and is very positive already, okay, then it will switch to positive. All right, so only when you're very sure that you won't change. Until you're very sure, then you change. If you're not so sure, then you don't change. That's the whole idea. All right, so this is H. And if this is A sine omega t, all right, this corresponds to a point that it changes. Let me draw things clearly so that it is easily seen. All right. Okay, so the part that correspond to here should be here. So here, at this point, I will call it omega T1. All right, this sine omega T, this would be the omega T axis. And here should be 2 pi. So here should be pi. All right, this should be the one that correspond to. So which means here should be omega T1. And it's obvious here when it is very positive should be, here should be pi plus omega T1. So now the question now is to find the describing function. So as before, the describing function do the Fourier series approximation, or I need to do a bit of maths first. Omega T, just basic algebra first because we need them, so we just do them first. Omega T1 is what? Omega T1 is actually angle sine inverse of, this is H over A. H over A. Basically, A sine omega, basically A sine omega T1 is equals to H. All right, this is the point here. A sine omega T1 is equals to H. So omega T1 will be this. Then just need to do some simple geometry. If this sine is always related to the right angle triangle, so if this angle is omega T1, then is opposite over hypotenuse, opposite over hypotenuse. This should be A square minus H square. So cosine of omega T1 must be equals to adjacent over hypotenuse. Okay, we just need to do this maths because we need it later on. All right, then come back. So we do the Fourier series integration. So the Fourier series integration is integrate over 2 pi whatever C times cosine to get A1. Now notice this signal here is no longer odd or even. So you don't have A1 equal to 0 or B1 equal to 0. You have to solve for both A1 and B1. So, and we try to be clever. We don't want to integrate over 2 pi. We just integrate over pi and multiply by 2. You see the formula is integrated over 2 pi and there's no multiply by 2. So if you integrate over pi for this interval, then your signal from here to here is just m. So it's taking an m here. So if you do the integration, you get this, then you get this. So that is done. Likewise, B1, you just apply you multiply by sine, that's the Fourier series formula. Then the signal is just m if you integrate over this interval. So if you do the integration, you just get this. And then if you this secondary school integration, you stick in all the things, you will get this. So finally, if you look at my lecture notes, the describing function, the formula is just B1 plus JA1 divided by capital A. So you just stick it in. And then this would be your describing function. So this would be the describing function that the practical one that will be used, because the relay in the industry when they implement will always include hysteresis because of noise. Okay, so now let's go to the next topic. Self-oscillating adaptive systems. Okay. All right, so far when I teach you the relay, we always talk about a sine wave. So when we look at the loop, we always say, okay, you have a sine wave, sustained oscillation going through. Now we'll consider, instead of just a sine wave, you have one more low frequency signal going through. So now, which means the signal that is going through this control loop is, in the past, we only analyze you have a sine wave. So A sine omega t, I just write here. But now, no, more than that, it will be A sine omega t, what I taught before, plus a B, which is a low frequency signal. All right, so now two signal is going through, a low frequency signal B and the old sine wave A sine omega t that I teach you just now. And to do maths, low frequency, what's the lowest frequency? Zero. What is zero frequency? DC. So to make life easy, all right, we do maths and we will then approximate this B, a low frequency, by DC signal. So which means we say, the signal going through here is a sine wave plus a DC signal. And the DC is an approximation of low frequency signals that are inside these loops. Okay, so if that's the case, we still can do basically describing function. So now the first thing is, so now since it's DC, so it's just not DC don't change with time. So B become just B. There's no B bracket T. All right, so B is the DC signal, then you have the usual sine wave. So if you draw a picture, then you will see that this would be the frequency that is going through the signal. And as before, there's a relay in the loop. So that's why when this signal is positive, the relay is plus D. When this signal is negative, the relay is minus D. You see the picture here. All right. There's a relay plus and minus D. So when here is positive, here will be D. When here is negative, this will be minus D. But the signal here has a DC plus an AC. And a DC plus an AC, you look at this picture here, is very obvious. This one is the AC, and this dotted line is the DC. So the AC is shifted above by the DC of value B. And the amplitude of the AC is A, as before. So this is A. So this is A sine omega t plus B. So this would be the signal. A sine omega t plus B would be this signal that goes inside the loop. All right, then the output of the relay is just as before. Positive D and minus D. If the signal is positive, if the signal is negative, it's just minus. All right, so given now two signal, we can write Y, the output, like that. The Y, the output, has a DC input multiplied by a DC gain all right. The relay we will still think of the relay as a gain. But because coming in has a DC input and an AC input, so we will say that the relay has two gain, a DC gain and an AC gain. So the relay output, all right, the relay output will now be the DC input multiplied by the relay DC gain and the AC input to the relay okay, AC input. I use the word AC is alternating current. So sine wave sometimes we call it AC. Just make it easier instead of saying sine. So AC is sine, DC is the DC signal. Okay, so AC input must be multiplied by AC gain. Okay, AC means sine wave. So B plus A sine omega t, DC input plus AC input, the DC multiplied by DC gain, the AC input multiplied by the AC gain of the relay will give you the output of the relay. All right. How to compute the DC gain? You just take the value, the DC value of the output. If you look at this picture here, DC value of the output divided by the DC value of the input. So the DC value of the input is Z. What is DC value of the input? B. All right. So what is the DC value of the output? You just find area under this curve. Or 2 pi. So this 0 from here to here is 2 pi. So you find this area, this area, this area. Area under a curve is DC value. Are you all with me? All right. So you find the area of this curve divided by the area of this. That will be the DC gain. All right. I don't know, you all look at me like that. So I just tell you some simple thing. If you have time here, if you have a voltage here, ask you what's the DC value, you will tell me it is like that, this one. Will you say that? All right, how you get that? All you need to do is find this area. All right. Find this area. Then if from here to here is T, then this area is A, then you will get this value here as A divided by T Are you all with me? Correct or not? That you will get the DC value of this signal, general signal, any signal, doesn't matter. You basically take the area under the curve divided by the duration, and that's it, that's the value. Okay, so likewise, find the area, divide by the duration, which is 2 pi. Find, so that is the input DC value, the output DC value, find the area. This one, area means divide by the durations, that will give you the output DC. So DC gain is output DC divided by input DC must be DC gain. So if you, the maths will then look like that. Nothing. All right. This says area. This is area. This is output area. This is also area. This is input area. So output area divided by input area, that would be the gain. And B is the DC gain. All right, then you know you look at just square. So you can look, it's very easy. You will find the R, you just do this. All right, and then you do the algebra, you get this, and then alpha. Alpha is angle whose sine is B over A, because this is alpha. All right. So this is B, this is A. You'll find that this angle here would be angle whose sine is B over A. So alpha is angle whose sine is B over A. This is secondary school trigo, so you go and take a look. So this would be the DC gain. Then AC gain is nothing. Just go and use the Fourier series that I teach you for the relay. This pure application of the Fourier series. Integrate the output y over 2 pi, divide by pi. That's it. Then you'll find this is the describing function that I teach you last time. Exact describing function, nothing new. All right, so you do that. They work out for you. So this is the AC gain. This formula is exactly the same as describing function for the relay that I teach you. All right, so now you have AC gain. Okay, so now if there's a B over A is small. Remember, B is the DC input, A is the AC input, the amplitude of the sine wave of the input. If B over A is small, then you look, the DC gain is given by this. You know small b over A, then angle whose sine is B over A is just B over A. So if that is the case, then B and B will cancel. Then it is just 2D over pi A. Okay. Then if B over A is small, so the base is 0. So if this is 0, then it's just 4D over pi A. It's approximation. All right, so if B over A is small, then the AC gain is 4D over pi A. The DC gain is just 2D over pi A. Now, the key results is in my next statement. You look, then say, hey, the key results of this research is that you see that, hey, this is always 2 times of this. 4D over pi A is 2D over pi A. So this is 2 times of this. So this is the key result. All right. The AC gain is always 2 times the DC gain. So this is the key result. And later on, the whole theory of this self-oscillating adaptive system rests heavily on this key result. Okay, if that's the case, then now we break up into, like, I think you all do engineering. If you have AC signal and DC signal in the circuit, you can do DC analysis and then AC analysis. Have or not? Have you all done that before? All right, you can break it up into 2 parts. Do AC analysis, DC analysis. Then the result can add back together because of superposition, that kind of thing. All right, so we split the result into 2 parts and look at the AC part. The AC part we do before. The AC part is like that. If you have a relay, where is it? The AC part, the relay is replaced by NA. Then you connect to a plant. Then you have this. Then I say this many times. Then you have this sine wave. And then you have this sine wave. If you have a relay, you will have sine wave oscillation. And I say this many times, N times G must appear to be -1. So this is the one of the result. This we have done it before. Then we look at the low frequency part. Okay, if it's a low frequency part, then we will have N, B, then we have G. Okay, low frequency is not the AC. The AC is the one that oscillates. Low frequency don't oscillate. So now, how? The loop gain is just the DC gain NB times GP. But what can we conclude about that? We look. Algebra will tell you, oh, this is this. Then if you look, all right, this is this. But we are saying that this is always half of NA. That was the key result. NA is equals to 2B, 2NB. So NB is actually half of NA. So NB is actually half of NA. That was the key result. Then another key result. This is 1 or -1. If you just consider a magnitude, it's just 1. So finally, the magnitude of the low frequency at this frequency is just 0.5. And what is this frequency? And what is this 0.5? If you all know this frequency omega u is this frequency here. All right, this gives you, this is A sine omega u t. At this frequency, all right, at this frequency, if you draw the Nyquist curve of this, you will draw the Nyquist curve of this. Nyquist curve will look something like that. Maybe I just draw it something like that. Okay. When this is -1, so this is -1. All right. And this here, the frequency is, and this one, if you draw, this should be N A G. That will be the Nyquist curve at omega u, or at different omega, you may have real part and imaginary part. At omega u, this will be exactly equal to -1 because of the max. This omega u would be the exact frequency here. Are you all with me? Okay, this is classical control when you all learn frequency domain. All right, this is Nyquist curve. This is J omega. So for different omega, you will have different point. Then when you reach omega u, which is this one, and G is exactly equal to -1, so you pass here. Then you have to look, hey, algebra just say, tell you that, where is it? NB G J omega u is equals to 0.5. So means if you think of the low frequency, the crossover at omega u would be at 0.5. So basically, you can think that if you draw the Nyquist curve of the low frequency one, you will draw it as NB G J omega. It will cross over at 0.5. As far as low frequency signal is concerned, the math says that it will cross here at 0.5. If you take, if the high frequency you draw like that, here at -1. Then we learn in classical control, this crossing gives you the gain margin. Gain margin is something that you will have to learn in, control engineering, the first course. So it's always inverse of this. So in this case, we will have this example. This will give us a gain margin of 1 over 0.5, which is equals to 2. If we cross over at 0.1, then has a gain margin of 10. So because the math says this is always equals to 0.5, so the low frequency gain margin is always 0.5. And in classical control, many years ago, when you first learned gain margin and phase margin, one way of designing a control system is to get a gain margin. you specify a gain margin, and it is typical to specify a gain margin of 2 or 3. All right, it's quite standard. If you design classical control, they will say, oh, design a gain margin of 2 for the control system, or design a gain margin of 3 for the control system. So now a gain margin of 2 is being designed for this. So all the things I've said is here. The key thing is that the amplitude margin or gain margin is 2. Okay, so now I think I say all these things so you don't have to imagine. Let's look at the MATLAB simulation and so on. Then you don't have to imagine things. Then things become clearer and clearer. So we use this same plan as before, relay oscillation. All right. If you stick in a relay, like that, let me see. Okay. Let me find a place to draw. Okay. So if you stick in a relay, like that, then you connect it to your plant G, then you have something like that. As before. So G, this G is the same as the previous example, relay oscillation. So previous relay oscillation is here. Previous example on relay oscillation is here. Fine. Now this one, example relay oscillation, we use the same plan. We calculated if you stick in a relay like that, then you oscillate omega u as root alpha. All right. Omega u is root alpha. So that would be the oscillation. Okay, so this one, like that, you will have oscillation of root alpha. Okay, if you have oscillation of root alpha, you stick that in, the magnitude of G should be this, which means you put at this oscillation, we put this as J omega, this J omega, this is J omega. I think this question says that alpha is 20. All right. So this will be root alpha. So you stick it inside here. You stick it inside here. Okay. You find the magnitude of this, it will give you this answer. Okay. So now, if that is the case, then we know the gain of this is given by this, and the question says that K is 3, D is 0.35, alpha is 20. So you stick that in. K is 3. Alpha is 20. So you stick that in. So this one should be equals to 3/21. So now the question say D is 0.35. So this here is, here you know you will get oscillation. You get oscillation here. This is 0.35. All right. And then since the amplitude here, what did we get is 21/3. So here, or here, we assume that here should be what I call E naught is equals to 21/3 times, this is 0.35. 0.35. All right, then I think the answer is 0.05. So you will get the sine wave oscillation here. So the sine wave oscillation here should be at 0.05.
So is it 3 divided by 21 or 21?
Is it which one? I also blur. What did I write just now? Oh, 3 divided by 21. Okay. Okay. So now, of course, then the oscillation here is the same as this, but it's upside down. So it's just 0.05. So now you look at the MATLAB simulation. You here, this is MATLAB simulation. This is D equals to 0.35. This is your E. Is E, I call it E naught, is equals to 0.05. All right. Now, what is the AC gain? You can calculate the AC gain. I call it NA. You look at the sine wave oscillation. The input is 0.05. the output, if we just pretend the square wave is a sine wave of amplitude 3,5, all right, for approximation, then you get output sine wave over input sine wave, and your AC gain should be 0.35 divided by 0.05, and this should give me 7. Approximately, my AC gain would be 7. I mean, if you are super accurate, then you can do Fourier series approximation to get this square wave into a sine wave, but let's not bother. Just say that the book also don't think amplitude of the sine wave or the square wave, they are the same. Then we say what? Hey, the DC gain, what is the DC gain? The DC gain T result is forever half of the AC gain. So this comes here, divided by 2. And because it is always half, the maths show you that this will have a gain margin of 2. So if you put a step input, you see that these are the typical step input in a gain margin of 2. Okay, there's a slight catch there. The simulation was done with a filter in front, so it was not done like that. Let me the unit step goes through a filter. So a unit step goes inside this filter. This filter is a standard filter, omega square over s square plus 2 zeta omega s plus omega square. All right. And the question says that zeta is 0.7 and omega, okay, I put it omega n equals to 1. So this is omega n, omega n, omega n. So this is 1. This zeta here is 0.7. So you have a unit step goes in. So the outcome of this low pass filter is a slow down step. So therefore, what goes into here is not just a sine wave plus, but you have a low frequency signal that comes from this part that goes into the loop. All right. And as far as this low frequency signal that goes into the loop from the set point change, it will have a gain margin of 2. And you will have this. All right. The step response will have that gain margin of 2. That is a standard step response to control system. Then the simulation say, oh, at t equals to 25 seconds, which means here, suddenly the plant change increased by 5 times. The plant gain increased by 5 times. So the adaptive control must adapt itself. So how does the adaptation work? When the plant increased by 5 times, that means that at first, this is 3. When it increased by 5 times, so now this must be 3 times 5 over 20 plus 1 must be equals to 15 over 21. So 15 over 21, you will have this one will be 15 over 21 times this. So now here the oscillation must be 5 times bigger. So 15 over 5 times, so is 0.25. All right, how I get this is because I got, what did we get? 15 over 21 times 0.35. All right, because this one now changed to just last time I wrote wrongly. Last time I wrote wrongly here. So I better change it. This previously was 3 over 21. So now increased by 5 times is 15 over 21. All right, that's why this is now 0.25. So now it will be much bigger. So this should be 0.25. Okay. So you see the signal now is 0.25 here. MATLAB will show you is 0.25. Then you see what is the AC gain. We calculate. There's a plant change at 25, so that's why you see the simulation at t equal to 25 start to change. So AC gain NA equals to, again, we look, this is the input, this is the output, 0.35. So I will get 0.35 over this one. (0.25). So if you simplify, this should be 7 over 5. All right, you see, previously the AC gain was 7. Now the plant increased by 5 times. The AC gain of the relay dropped by 5 times. And the DC gain of the relay, NB, is always the DC gain, is always the AC gain divided by 2. So this. So you compare with this, the DC gain also dropped by 5 times. So now you see that where the adaptation is, plant gain increased by 5 times, the relay which provide the AC gain and the DC gain for the signal dropped by 5 times. The number show you that. All right, the number shows you that. AC gain was 7. This one, plant here increased by 5. AC gain becomes 7 over 5. So, which means plant increase, the controller gain decrease, then cancel each other, then the loop gain is the same. The loop gain is the same, which means if you draw the Nyquist curve, this times this is the same as before, and you have a gain margin of 2, no change. So that's why you see the simulation. When they make a step, this step response basically looks like this step response. Gain margin of 2. Approximately, right? Because approximation are made. And so, okay, I will stop here tonight. I think you let the concept sink in. Next week, I will continue with this self-oscillating adaptive system. This is not usable, you like that. Whereas next week, we will modify the whole system until, you see, then it's so nice. Okay, but the concept is the same. So before we go into the detail, we'll let the concept sink in. All right, I see you next week. Okay, bye-bye.